What if the universe played the cruelest trick imaginable? One moment, the sun shines exactly as it always has, warm, bright, steady. The next, without warning, it collapses into the single most mysterious object in existence, a black hole. No explosion, no flash, no sound, just an instant transformation of the object our entire world depends on. And here's the part that makes this scenario so unsettling. Despite everything you think you know about black holes, Earth's orbit wouldn't immediately change. In fact, nothing would move at all. But everything else, everything that makes life possible, would begin to unravel. Every moment of our lives, every breath, every green leaf, depends completely on that nuclear powerhouse at the center of our solar system. The gravitational pull that holds our entire solar system together depends only on the total mass of the central object and the distance between that object and the orbiting bodies, like Earth. Our Sun currently has one solar mass. If the black hole that replaces it has precisely the same mass, one solar mass, then the gravitational force it exerts on Earth, Mars, Jupiter, and every other orbiting planet remains exactly the same as it was a moment before. The basic rules of orbital mechanics remain stable. Earth would not suddenly spiral inward, and it would not be thrown violently out of its path. Our planet would continue following its familiar, stable, elliptical orbit around the newly formed black hole, just as it did around the Sun. The outer solar system planets like Jupiter and Saturn would also continue their paths unchanged, completely unaffected by this switch in central objects. This stability in orbit is the one piece of good news in this cosmic catastrophe. However, the size difference between the objects is wildly dramatic. The current Sun is a gigantic ball of hot gas, measuring nearly 1.4 million kilometers across. If that mass was somehow compressed down to the necessary density to form a black hole, the resulting object would be astonishingly compact, possessing a radius of only about 3 kilometers. That is roughly the size of a small town. This tiny dark sphere would sit right where the colossal Sun used to be. For all practical purposes, from 150 million kilometers away, this tiny object feels exactly the same gravitationally. The concept that the Earth could orbit an object the size of a small town and still maintain its comfortable distance seems completely bizarre, but that is the reality of gravity. The problem, however, arises from everything else the Sun provides besides gravity. The destruction begins not with an immediate gravitational pull, but with the instantaneous loss of light and heat. The Sun produces tremendous amounts of light and energy through nuclear fusion reactions happening deep within its core. A black hole, by its definition, is an object from which no light can escape once it crosses the border known as the event horizon. It is fundamentally dark. It generates no energy of its own, unless it is actively consuming surrounding material. Assuming this black hole appears instantly, replacing the Sun, there is no gas or dust immediately available for it to consume. It is initially a quiet black hole, consuming nothing. For us on Earth, the final warning is visual. The light that was already traveling through space from the Sun when it vanished will continue its journey for the next 8 minutes. That final golden radiation washes over us, and then suddenly it stops. The sky goes absolutely terrifyingly dark. The moment the light goes out marks the absolute end of the surface world we know. The loss of constant, massive stellar radiation immediately triggers a rapid and irreversible decline in Earth's temperature. The thermal energy currently stored in our atmosphere, oceans, and land begins to escape into the void, leading to a planetary freeze-out. In the minutes immediately following the darkness, the catastrophic consequences for life are immediate. Photosynthesis, the process that fuels nearly all complex life on Earth, stops instantly with the disappearance of sunlight. Plant life loses its energy source, signaling the beginning of the collapse of the entire surface food chain. The timeline for planetary freezing is remarkably fast. In the first week, the exposed surface areas begin their rapid thermal descent. While the oceans act as a massive buffer against quick temperature shifts, the constant dissipation of warmth into space soon takes hold. Without the Sun's energy input, the global temperature quickly drops, setting the stage for massive planetary-scale chaos as surface moisture freezes. Within the first month, the average global temperature would plummet dramatically. Although the deep oceans would hold residual heat for centuries, the planet's surface layers and shallow waters would freeze over completely. Exposed air and land temperatures would fall far below freezing, making the terrestrial surface completely hostile to life. Within a year, if the atmosphere remains intact, which is a big if as we'll discuss, the thin band of breathable air around us would be critically cold. The loss of heat and the immediate lack of stellar input means our atmosphere can no longer sustain liquid water or habitable temperatures. The atmosphere itself faces a complex demise. Normally, the upper atmosphere expands when heated by the sun. While the sun is gone, the intense gravitational pull of the Earth maintains a grip on the remaining gases. However, with the total thermal equilibrium shattered, the temperature collapse could cause the atmosphere to condense and lose buoyancy. As the planet's surface cools radically, the atmosphere loses its energy source and becomes incredibly dense and cold near the ground, rapidly accelerating the freeze. For humanity, mass survival on the surface becomes physically impossible within weeks due to the cold and the resulting food chain collapse. Our only option for survival is to instantly replace the complex energy and life support systems provided by the sun with self-sustaining artificial infrastructure. The core challenge for humanity becomes adapting to the sudden eternal night by living permanently underground, powered by energy sources that do not rely on stellar radiation. The question of how long humans could survive is entirely dependent on our prior planning and ability to establish self-sufficient underground facilities. Survival is not a question of years, but whether certain crucial resources are immediately available. Without constant, massive solar energy input, life on Earth is restricted to highly specialized, self-contained habitats. For humanity to survive past the first few weeks, they must successfully retreat to deep, sealed bunkers or underground bases where geothermal or artificial power sources maintain a life-sustaining temperature and environment. The fundamental clock ticking against us is the biological need for food and water. Humans can only survive weeks without food and days without water. Any protected population must have access to massive, secured stores of resources, or, more realistically, must establish totally independent agriculture. This immediate necessity points toward nuclear power as the single essential solution for replacing the sun. Nuclear reactors, which convert mass into energy, require no external stellar input, making them the only practical long-term energy strategy for sustained human survival. This mirrors the planning for long-term human presence on Mars, where self-reliance is founded upon securing infrastructure, including power and resource recycling. An adapted human civilization would depend on three things. 1. Thermal stability. Deep underground facilities are naturally shielded from the extreme surface cold, accessing warmth from the Earth's core. 2. Artificial photosynthesis. Sustainable food production would require elaborate subterranean hydroponic farms, relying entirely on nuclear-powered artificial lighting to replace the solar energy essential for crop growth. 3. Water recycling. The remaining water resources must be recycled almost perfectly. Systems already planned and operational on the International Space Station, ISS, achieve high levels of water purification and recycling, up to 90%, but a truly isolated community must aim for near 100% recycling to guarantee generations of survival. The transition to a subterranean existence would not be easy. It requires instantaneous, coordinated construction and movement of populations into hardened, life-support environments. The complexity means only isolated pockets of humanity, already possessing the infrastructure and technical ability, would have any realistic chance of long-term survival. Their persistence would rely entirely on maintaining highly complex mechanical systems and perfectly balanced ecosystems for closed-loop survival. The true longevity of humanity in this scenario, assuming this successful retreat, is theoretically unlimited, but entirely dependent on the durability of the artificial power and life support technology they can sustain. So far, we have only discussed orbiting a quiet black hole, one that is completely dark and passively waiting. But black holes become visible and monstrously powerful when they begin consuming matter. This process of consumption involves forming an accretion disk. An accretion disk appears when gas, dust, or an object, like a distant asteroid or comet, falls into the black hole's immense gravitational field. Because this material usually has rotational energy, it does not fall straight in. Instead, it swirls rapidly around the object, creating a flat, disc-like structure. The key physics here is friction. As the gas and particles in the disk swirl inward, friction between the material moving at different speeds causes the gas to heat up intensely. This superheated gas begins to glow. This accretion process is exceptionally efficient at converting energy into radiation, far exceeding the efficiency of stellar fusion. Nuclear fusion converts less than 1% of mass into energy, whereas accretion onto a black hole can convert gravitational potential energy into destructive radiation at rates sometimes exceeding 40%. If matter begins actively feeding the black hole at the sun's core, it instantly transforms into a terrifying cosmic engine known as an active galactic nucleus, AGN, or if distant and extremely bright, a quasar. This transformation means immediate death by fire, not slow death by ice. If enough material formed a sufficient accretion disk, the energy released would likely make the black hole far brighter than the original sun, bathing Earth in lethal high-energy X-rays and gamma rays. This radiation would instantly strip away our fragile, compromised atmosphere and vaporize the surface. Furthermore, active black holes can launch jets, highly focused streams of ionized matter and energy accelerated close to the speed of light, often directed perpendicularly away from the accretion disk. These astrophysical jets are powered by the enormous energy released near the black hole, possibly extracted from the black hole's own rotation and twisted magnetic fields. If Earth were caught in the path of one of these jets, the vaporization would be instantaneous. However, since our solar system is relatively clean and quiet, the likelihood of a massive accretion disk forming immediately is small. The sun's quiet, dark replacement suggests that the primary struggle for survival remains the cold and darkness, unless a large, distant gas cloud or planet falls into the void later on. The possibility of forming such a disk reveals a profound observational difference between black holes and neutron stars, supporting the idea of the event horizon. Neutron stars, the densest objects next to black holes, have a physical surface. If gas falls onto a neutron star, it crashes into that solid surface, instantly converting all its energy into thermal radiation, making the neutron star extremely bright, sometimes 100 times brighter, during accretion. A black hole, conversely, has an event horizon but no surface. When matter falls into a black hole, the energy is swallowed and is not re-radiated, resulting in a much dimmer overall glow compared to an accreting neutron star. This difference confirms the existence of that final boundary, the one-way door of the event horizon. If humanity does succeed in retreating underground and creating its artificial, self-sustaining world, they would occasionally look up at the void where their primary star should reside. What would the new sky look like without the sun's overwhelming presence? The visual experience would be dominated by perpetual, stunning night. All the stars of the galaxy and the faint glow of the Milky Way would be visible 24 hours a day, unimpeded by solar glare. However, the invisible black hole at the center would still warp and distort the space around it, acting as a massive, powerful gravitational lens. Albert Einstein's theory taught us that gravity bends light because mass tells space how to curve and space tells light how to move. The light from stars directly behind the black hole would be radically bent toward Earth, making the invisible object visually present in a terrifying way. Instead of seeing empty darkness, observers would witness the light of background stars stretched into strange, shimmering arcs and bright, distorted circles surrounding a central dark region. This dark central region, the event horizon, would appear as a perfect sphere of absolute blackness, defined by the edge where light simply vanishes. This visual effect is known as gravitational lensing. The gravitational field would not only bend light, but also distort the perception of time near the object. If someone hypothetically fell toward the black hole, an observer far away would see time appear to slow down for the falling person as they approach the event horizon, confirming that gravity affects the very metric of space and time itself. If the black hole remained quiet, the sky would be a continuous celestial spectacle, an eternal night of stars centered on a tiny, silent, perfect sphere of dark blackness ringed by light bent by its own immense, unseen gravity. The Earth, preserved by human ingenuity, would be a cold, engineered bubble of life, silently tracing its orbit around a cosmic mystery. If we continue to focus on the human survival period, the core problem remains replacing the astronomical power output of the Sun with artificial sources on a planetary scale. The infrastructure failure rate, given the immense scale of transfer, would determine the ultimate survival time of any community. The challenge is not just powering light and heat, but sustaining the entire global environment and all connected technological systems. Without solar input, the global power grid, largely dependent on solar or connected fossil fuel systems that rely on surface logistics, would crash almost immediately. This is not a partial blackout, this is a total grid failure worldwide within days. Any long-term human survival plan must isolate the community from the surface failure and rely on power sources that are fundamentally shielded. Deep nuclear fission reactors are the only realistic solution, providing continuous energy for geothermal heating systems, food production, and air-water recycling. To establish and maintain these underground habitats, the surviving population must rely on the principles of closed-loop architecture. This principle ensures that no matter or energy is wasted, mirroring the high-efficiency systems needed for long-duration space missions. Food and air self-sufficiency. Since the massive food supplies required for billions cannot be stored, the surviving communities must rely on generating food through controlled environments. This requires perfect regulation of temperature, humidity, and the atmosphere. The atmosphere must be constantly scrubbed of carbon dioxide produced by the inhabitants, and fresh oxygen must be generated, often through the same process of water electrolysis that produces oxygen on the ISS Material Resilience. The ability to survive long-term also depends on resource production. Since resupply from a dead surface world is impossible, the underground community must develop autonomous production capabilities, including manufacturing tools, equipment, and spare parts. Without the ability to maintain the complex systems required for survival, the community will slowly decay as vital components fail. Ultimately, the human survival period depends on technological complexity and maintenance cycles. If a highly advanced society already had self-sustaining, nuclear-powered underground complexes ready, perhaps mimicking the complex infrastructure plans for Martian colonization, survival could extend indefinitely. Otherwise, the complex logistical and political challenges of moving billions of people and their essential food/power infrastructure underground in the face of planetary cold guarantee widespread and rapid collapse of civilization on the surface. To fully appreciate the threat of the accretion disk, we must look deeper into the physics of how black holes convert gravity into light and why this process is so much more efficient than anything else in the universe. The black hole itself is dark, but the friction within the accretion disk generates immense heat. This heat transforms the matter into plasma, causing it to emit powerful X-rays and visible light. This conversion is not due to nuclear fusion, it is due to gravity. The energy released is the conversion of gravitational potential energy into kinetic energy, motion, and then thermal energy, heat, through friction. The sheer efficiency of this process is what creates objects as bright as quasars. When stars fuse hydrogen, they convert less than 1% of the hydrogen mass into usable energy. However, as matter spirals toward a black hole, the conversion of gravitational energy into radiation can approach the theoretical limit of 42% of the mass energy. This incredible efficiency is why a tiny accretion disk around a black hole can outshine a galaxy containing billions of fusing stars. This immense radiation output presents two specific threats if a disk were to form. One, high-energy sterilization. The light emitted from the innermost hottest region of the accretion disk is high-energy radiation, including X-rays and gamma rays. If this disk formed, Earth would be bathed in an intense flood of radiation that would instantly sterilize the planet and strip away the atmosphere. 2. Size confirmation via flickering. The light produced by an active accretion disk is not steady. It varies quickly, sometimes flickering hundreds of times per second. This rapid change in brightness is an important scientific tool because it immediately restricts the maximum size of the emitting region. The physical size of the X-ray source cannot be larger than the distance light travels during that short interval. This observational proof confirms that the source of power is incredibly compact, much smaller than any star. If the black hole replaced the Sun, and if by some terrible chance it began consuming enough matter quickly, the accretion disk would become a highly dynamic system. The constant turbulence in the disk, driven by viscosity and magnetic fields, would feed the monster, creating powerful winds and jets. The accretion-powered black hole is not merely a dark presence, it is an engine capable of immense destruction, which happens to be the most efficient energy conversion machine in the universe, turning gravity into destructive light. Let us return to the quiet scenario, the dark sky view, and review the final, stable state of the system based purely on physics. If the black hole remains quiet, Earth would be locked in its stable, safe orbit. This is because far away from a black hole, the gravitational pull acts exactly as if it were still the Sun. It behaves as a point mass, exactly following Newtonian physics. It is only close to the object where general relativity effects take over, causing the dramatic warping of space-time. The appearance of the sky would be completely transformed by the process of gravitational lensing. If you want to understand space, like a NASA-level analyst, quick without studying for years or paying thousands for a university degree, we have a community that will help you. Link is below. A black hole dramatically warps the space around it, making it act like a powerful lens. Light rays coming from distant stars that pass near the black hole are bent and focused toward us. When viewing the black hole's location, the sky would feature one total darkness. The Sun's absence means the sky is permanently dark, revealing the Milky Way and all distant stars 24 hours a day. 2. The black shadow. The event horizon itself would appear as a perfectly circular, absolute blackness because no light from within that radius escapes. 3. Warped starlight. Light from stars positioned directly behind the black hole would be stretched and distorted into bright, arcing patterns around the edge of the black circle. This tiny, quiet object would dominate the sky, not by shining, but by silently distorting the light of everything behind it, serving as a constant visual reminder that the metric of space-time is profoundly curved at the center of our solar system. In this scenario where orbital mechanics are maintained, but light is absent, the long-term question of Earth's ultimate survival is not about gravitational destruction, but about energy and adaptation. We would survive only as long as our technology could sustain an isolated underground civilization. To compare this ultimate end with other extreme possibilities in the cosmos, you must look at worlds capable of sustaining life under pressures far greater than our own. Click here to see What If We Lived on a Super Earth video. I'll see you there.